In the first part of this lesson, we are going to look at, as it says here, velocity-dependent forces, often referred to as a drag force problem. And let's see the details. So, as it says here, we have our skydiving cat without a parachute in a free fall type of motion, so no parachute. But we are allowing for air resistance, and we're being told that the air resistance is directly proportional, so V to the first power. So directly proportional means that the air resistance will be linearly proportional with the velocity, and it's given by drag force equals a proportionality constant B, which we're going to talk more about, times V, and we're assuming that this cat started falling with zero initial velocity. So the first thing we are asked to do is to simply draw the free body force diagram. So we take our cat over here, and hopefully this part is okay. We have mg down, and the only other force is our velocity-dependent drag force, BV, resisting the motion downward. Well, we are told in part B to write down the differential equation of motion. And notice I have that highlighted because that's language we need to be familiar with. Differential equation of motion for us means F equals ma is the go-to equation to get this differential equation of motion. Specifically, we are going to take the acceleration and do one of two things with it. We are either going to, as we do here, make it into dv dt, or in a different type of problem, if the force was proportional to position, we would change it to d squared x dt squared. I'm not writing that here because that's not part of this problem. So we do what we always do with our sum the forces and our force arrows. We have bv up, we have mg down, and notice we have to have the negative here because the mg is going to win out at least up until the point where the bv can get big enough to balance, and we'll talk more about that in a moment. So bv minus mg equals negative ma. We change the a to dv dt, and that is it. We are done. That is the differential equation. So this is the differential equation that governs or describes that motion. Well, now we are going to be asked to, whoops, let me erase that, derive an expression for the cat's maximum velocity. Well, let's take a look at what it says here, and please get this part down because this is really important. We're going to look at our force diagram and look at those values and think about what is going on here. Well, if the cat started from rest, that means that BV is 0 because V is 0. So initially, the cat is in, technically, free fall motion, only acceleration due to gravity, 9.8 meters per second squared down. But as soon as the speed begins to increase, BV begins to get bigger. And it gets bigger and bigger and bigger until BV equals mg. That's the limit. It can't get bigger than mg because friction is never, that air resistance friction is never going to pull it back up. So when it equals mg, that is it. We're done. The speed is no longer increasing. We have reached the maximum value. That maximum value in this type of a problem is called terminal velocity. So you are at the term limit that you can get to. That happens when, as we said, no more acceleration. And look, mg equals bv, v equals mg on b, and we have an expression for the terminal velocity. So this is kind of a new way of looking at how friction affects, in this case, air resistance friction affects motion. It's a velocity-dependent force, so it's a little more complicated mathematically. And the last comment on this page of notes for you to absolutely make note of is this is not a constant acceleration problem, right? Do not use constant acceleration equations with a drag force problem because look at this equation, right? The acceleration, right, is going to be dependent on velocity. It is not constant, no constant acceleration equations. So let me clean up my annotations here for you. I will pause the page. Make sure that you get all of these annotations down completely, and we'll move on with this analysis.